Question 25 of exercise 13.1.
f of x is absolute value of x divided by x, comma x not equal to 0 and 0 when x is equal to 0. This is the definition of signum function, and we have to find limit extending to 0 of f of x. Here we don't have x greater than or equal to 0 or x less than 0 definition, but we have absolute value function. Absolute value of x is x when x is greater than or equal to 0, and it becomes minus x when x is less than 0. So absolute value function has two different definitions at 0. Therefore, we will do LHL and RHL. LHL, limit extending to 0 minus f of x. Here if you see, this function is not defined at x is equal to 0. I cannot substitute x as 0 in this function because the function is not defined at x is equal to 0. We can only approach 0 from both the sides, left hand side, right hand side. I can go closer and closer to 0. I can calculate the function value, but I cannot substitute the value 0 for x in this case because the function is not defined. Okay, let us remove the absolute value sign. For 0 minus is on the left side of 0. Very close to 0, but on the left side of 0. The value will be negative, we know, on the left side of 0. For negative values, the absolute value function is minus x. And the denominator is already x. And it becomes minus 1, which is a constant. Therefore, if you apply the limit for constant, it remains the same. The answer is minus 1. Similarly, let us calculate RHL. Limit extending to 0 plus f of x. The same f of x we use because x approaches 0 here. It cannot take the value 0. F of x is 0 when x is equal to 0, we cannot use. X not equal to 0 definition has to be used because x only approaches 0 in this case. Same function, absolute value of x by x. When x approaches 0 from the right side of 0, very close to 0, but from the right side of 0, the value is positive. The value which I am going to try are all positive values. So let us use absolute value function definition. Absolute value of x for positive values of x is x. See the definition of absolute value of x for x greater than or equal to 0, which becomes 1. It is a constant. So limit of a constant is the same number, 1. Now LHL and RHL are not equal. Therefore, limit extending to 0 of f of x does not exist. Why it does not exist? We know the graph of this function, signum function. When it is 0, the answer is 0. And for all positive values, the answer is plus 1. And there is a bubble here because it is not defined.
At x is equal to 0.
And for all negative real values, the answer is minus 1. And there is a bubble here because for x is equal to 0, the answer is 0 here. See, there is a gap here in the graph. That's why LHL and RHL are not equal. When there is a gap in the graph, LHL won't be equal to RHL. For every function, we cannot draw the graph and check whether the limit exists or not. So we use this algebraic method. Question 26. F of x is equal to x divided by absolute value of x. It is similar to that signum function. Same method we are going to follow. And we have to find limit extending to 0 of f of x. Absolute value function has two different definitions. Absolute value of x is x when x is greater than or equal to 0, and it becomes minus x when x is less than 0. Let us find LHL. Because we have two different definitions for absolute value function, we need to do LHL and RHL. LHL is limit extending to 0 minus f of x. Here x tends to 0 because x cannot take the value 0 in this function x divided by absolute value of x. So we can only go closer and closer to 0 value, remember that, because the function is not defined at x is equal to 0. So we cannot substitute directly x as 0 in this question. Okay, let us remove the absolute value sign. We know that x approaches 0 from the left side of 0. So very close value on the left side of 0 will be negative. So for negative values, absolute value of x is minus x. Look at this definition. This ratio is minus 1. Limit of a constant is the same constant, minus 1. Now let us calculate RHL. Limit extending to 0 plus f of x. So in this case also, x approaches 0. The function is not defined at 0. Let us remove the absolute value function. Here x approaches from the right side of 0, very close to 0, but the value is on the right side of 0. We know that those values are positive. Therefore, absolute value of x is x. This ratio becomes 1. Limit of a constant is the same constant. So in this case also, LHL and RHL are not equal. Therefore, limit extending to 0 of f of x does not exist. Question 27. Find limit extending to 5 of f of x, where f of x is absolute value of x minus 5. Absolute value function has two different definitions. It is x when x is greater than or equal to 0 and minus x when x is less than 0. But I have told you, if you have only absolute value function, LHL and RHL will be the same. But since we have two different definitions, we will do LHL and RHL. So LHL is limit extending to 5 minus. We have to find the limit at 5. And the definition of f of x is absolute value of x minus 5. Okay, it's 5 minus. That is on the left side of 5. Left side of 5, for example, let us take 499999, which is a positive number. All values on the left side of 5, which are very close to 5, will be positive. I can write it as x minus 5. And it is a polynomial. Again, I am repeating, polynomials are defined for all real values. We can directly substitute the limit value. Whether it is 5 minus or 5 plus, directly we can substitute 5. So 5 minus 5 is 0. So LHL is 0. Let us do RHL. Limit extending to 5 plus f of x. The same definition. Limit extending to 5 plus absolute value of x minus 5. 5 plus means on the right side of 5. For example, 5.000001, which is positive. On the left side of 5 as well as on the right side of 5, both values are positive only. Very close to 5 you have to consider. So it becomes again x minus 5. I am substituting the limit value because x minus 5 is a polynomial which is defined for all values. This polynomial is defined for 5 also. Not only for right side values of 5, for 5 also it is defined. So we can substitute the limit value. This is also 0. So LHL and RHL are equal. Therefore, the limit exists and the limit value is 0.
In this question, both 5 minus and 5 plus are greater than or equal to 0. So we use the same definition of absolute value of x, which is x. So we could have combined LHL and RHL and done as one limit.
Question 28. Function f of x is a plus bx when x is less than 1 and 4 when x is equal to 1 and b minus ax when x is greater than 1. And it is given that limit extending to 1 of f of x is equal to f of 1. What are the possible values of a and b? So at 1, the limit value is 1 here. At 1, the definitions are different. For less than 1, for greater than 1, the definitions are different. So we need to do LHL and RHL. LHL is equal to limit extending to 1 minus f of x. Limit extending to 1 minus less than 1 definition we have to use, because x approaches 1 from the left side of 1, very close to 1 but left side of 1. So less than 1 definition, which is a plus bx. This is a linear polynomial. Polynomials are defined for all real values, so it is defined at 1 also. Directly we can substitute the value 1. LHL is a plus b. Let us find RHL. Limit extending to 1 plus f of x. So for 1 plus, we have to use greater than 1 definition, which is b minus ax. Again, this is a polynomial which is defined at 1. We can substitute the limit value, which gives us b minus a. Limit extending to 1 of f of x is equal to f of 1. This equation is given. So when do we say that the limit at 1 exists? Only when LHL is equal to RHL. Therefore, LHL equal to RHL is equal to f of 1. LHL is a plus b. RHL is b minus a. And f of 1 is given as 4 in the question. See the definition? So when x is 1, f of x is 4. Now we have two linear equations in a and b. A plus b equal to 4 is one equation. B minus a is equal to 4 is the other equation. Let us solve these two equations. I am adding these two equations. A and minus a are getting cancelled. 2b is 8. Therefore, b is 4. Let us substitute in the first equation. B value is 4. Therefore, a is 0. So, a is equal to 0, b equal to 4 are the answers. Question 29. Let a1, a2, etc. an be fixed real numbers and define a function f of x as x minus a1 into x minus a2, etc. x minus an. What is limit extending to a1 of f of x? Let us write f of x, which is x minus a1 times x minus a2, etc. Last term is x minus an. Let us apply the limit value. This is again a polynomial. We don't have any problem with polynomials because polynomials are defined for all real values. apply the limit value. Once you apply the limit value, no need to write this limit extending to a1. Here it becomes a1 minus a2, etc. The last term is a1 minus an. This term becomes 0. So 0 into any number will be 0. Therefore, the answer becomes 0. Now the second part of the question, we need to find limit extending to a of f of x. Let us write the function f of x. F of x is x minus a1 times x minus a2 times etc. Last term is x minus an. This is a polynomial. We can directly substitute the limit value. When you substitute the limit value, no need to write this limit. So it becomes a minus a1 times a minus a2, etc. The last term is a minus an. This is the answer. Question 30. If f of x is equal to absolute value of x plus 1 for x less than 0 and 0 for x is equal to 0 and absolute value of x minus 1 for x greater than 0, for what values of a does limit extending to a f of x exist? We will do cases here. Case 1, we will first check at x is equal to 0. We need to do LHL RHL because we have less than and greater than 0 definitions. LHL is limit extending to 0 minus f of x. For 0 minus, we use less than 0 definition, which is absolute value of x plus 1. 0 minus, approaching 0 from the left side of 0. So the values are negative. For negative values, absolute value function is minus x. And this is a polynomial. Directly we can apply the limit value. We get 0 plus 1, which is 1. RHL is limit extending to 0 plus f of x. For 0 plus, we use greater than 0 definition, which is absolute value of x minus 1. For positive real values, we remove the absolute value sign by writing plus x. Apply the limit. 0 minus 1 is minus 1. LHL and RHL are not equal. Therefore, limit extending to 0 of f of x does not exist. Now we have to check for the other real values. Case 2, we will check for all negative real values, that is a belonging to minus infinity to 0 open interval. Here a is negative, so we need not do LHL RHL. We can combine and do it as limit extending to a of f of x. Here we know that a is negative. So for negative values, the definition is absolute value of x plus 1. For negative values, absolute value of x is minus x. Substitute the limit value, which is 1 minus a. There is a limit value, that means the limit exists. Exists for all a less than 0. Now case 3, we will check for all real values which are greater than 0. That is a belonging to the open interval 0 to infinity. We need not do LHL RHL. We can combine and do it as one limit. Limit extending to a of f of x. But in this case, a is positive. So for positive values, the definition of f of x is absolute value of x minus 1. and for positive real values, absolute value of x is x. Apply the limit a minus 1. So this also has an answer. Therefore, limit exists for all a greater than 0. Therefore, the given limit, that is limit extending to a of f of x, exists for all a not equal to 0.
Question 31. If the function f of x satisfies
Limit extending to 1 of f of x minus 2 divided by x square minus 1 is equal to pi. Evaluate limit extending to 1 of f of x. We have two methods to do this question. One is we can take the limit of the denominator to the other side and we can prove this, or let us factorize the denominator. For rational expressions, we always do factorization. Because of this factor, the denominator is becoming 0. We are not able to apply the limit.
but the limit exists.
The answer is pi, it is given. So x minus 1 should be a common factor which gets cancelled. Therefore, x minus 1 is a factor of f of x minus 2. By remainder theorem method, f of 1 minus 2 should be 0. The remainder should be 0 because x minus 1 is a factor. Therefore, f of 1 is equal to 2. We have to find limit extending to 1 of f of x. Substitute the limit value, it becomes f of 1. And we know the answer for f of 1, which is 2. The answer is 2. Question 32. F of x is equal to mx square plus n, where x is less than 0, and nx plus m for 0 less than or equal to x less than or equal to 1, and nx cube plus m where x is greater than 1. For what integers m and n does both limit extending to 0 of f of x and limit extending to 1 of f of x exist? So let us find limit extending to 0 of f of x. We need to do LHL RHL because at 0 the definition has been split. Let us do LHL. Limit extending to 0 minus f of x. For 0 minus, we need to use less than 0 definition. Less than 0 definition is the first one, which is mx square plus n. This is a polynomial. We don't have any problem with polynomials. It is defined at 0. So directly we can substitute 0 value. M into 0 is 0. 0 plus n is n. Let us find RHL. Limit extending to 0 plus f of x. So we need to use greater than or equal to 0 definition. The second one. Extending to 0 plus nx plus m. This is a linear polynomial. It is defined at 0. We can substitute directly 0. So 0 plus m is m. And the question says that this limit exists. That means LHL must be equal to RHL. then only the limit will exist. N is equal to m. Therefore, limit extending to 0 of f of x exists when n is equal to m. Now let us check for limit extending to 1. Limit extending to 1 of f of x. At 1 also we have two different definitions for less than or equal to 1 and greater than 1. So we need to do LHL, RHL. LHL is equal to limit extending to 1 minus f of x. Less than 1 definition we have to use, which is the second one, nx plus m. Polynomial, directly substitute the limit value 1. So it becomes n into 1 plus m. Now RHL, limit extending to 1 plus f of x. Limit extending to 1 plus, we have to use greater than 1 definition, which is the third definition, nx cube plus m. Substitute the limit value directly, x is 1, n into 1 plus m. So limit exists, that means LHL must be equal to RHL. N plus m is equal to n plus m. Therefore, limit extending to 1 of f of x exists for any integral values of, it is given that they are integers, for any integral values of m and n, whatever values they take, n plus m is equal to n plus m. So n and m can take any value.
Let us learn about exponential and logarithmic functions, the supplementary portion of Limits and Derivatives chapter.
Any constant raised to a variable is called an exponential function. And here we are going to use e power x. E is a constant, it is an irrational number. It is called Euler's number. And the value of e is 2.71828, etc. And this e power x has an expansion. It is a series which is 1 plus x square divided by 2 factorial plus x cube divided by 3 factorial plus etc. up to infinity, where x belongs to R. And the graph of exponential function is, x can take any real value, and we know that e power 0 is 1. Therefore, when x is 0, y takes the value 1. The graph passes through this point 0, 1, and e power 1 is e, which is approximately 2.7. Somewhere here it will be. So the curve is going to be like this. This is y is equal to e power x curve. So the curve goes closer and closer to x-axis, but it doesn't touch the x-axis. And limit formula for exponential function is limit extending to 0 of e raised to x minus 1 divided by x is 1. We need not learn the proof of this. Now let us see the logarithmic function. Log of x to the base e. It is written as ln of x. In NCERT textbook, log x to the base e is written as log x. If base is not written, it means to the base e in NCERT math textbooks. This logarithmic function and exponential functions are inverses of each other, and the domain for exponential function is R. And let us discuss the range of exponential function. E raised to x is always greater than 0. E power 5 is positive, and e power minus 5 is also positive because it can be written as 1 divided by e power 5. So exponential function is always greater than 0. So positive real values. For exponential function, R is the domain and R plus is the range. So for logarithmic function, this becomes the domain, which is R plus, and range becomes R. Therefore, for logarithmic function, the domain is R plus and range is R. The log function is defined only for positive values of x greater than 0. But log x answer can be positive or negative. If we draw the graph of log x function, log 1 is 0 because e raised to 0 is 1, and log 0 is not defined because x should be greater than 0 for log x function. Log 1 is 0, so 1, 0 is a point of the graph. As you increase the value of x, log value increases, and if the value is less than 1, log x takes negative values. So the graph is like this. And if you draw y is equal to x line, so y is equal to e power x graph and y is equal to log x graph, they are images of each other with respect to the line y is equal to x. Therefore, they are inverse functions of each other. Log of e raised to x to the base e becomes x. And e raised to log x becomes x. Because log and e are inverse functions, they cancel each other. Therefore, the answer becomes x. Here also e and log functions cancel each other as they are inverse functions. The answer is x. Now the limit formula for logarithmic function is limit x tending to 0 of log of 1 plus x divided by x is 1. Again, we need not learn the proof of this. We have a series for logarithm also. So log of 1 plus x is x minus x square divided by 2 plus x cube divided by 3 minus x power 4 divided by 4, etc. In this series, x can take values between -1 and 1. 1 is included. Now let us do the supplementary exercise using these two limit formulae. Exercise 13-2. Evaluate the following limits if exists. First question, limit x tending to 0 of e raised to 4x minus 1 divided by x. We have this limit formula. To use this limit formula, we should have the same terms here. I have 4x here, therefore I need 4x in the denominator. Let us multiply and divide by 4. As x tends to 0, 4x also tends to 0. 4 times limit x tending to 0 of e raised to 4x minus 1 divided by 4x. By that limit formula, it becomes 1. Therefore, the answer is 4. Second question. Limit extending to 0 of e raised to 2 plus x minus e square divided by x. Limit extending to 0 of, we can separate this power as e square into e raised to x minus e square divided by x. E square is a constant. We can take it out. We can remove it outside the limit also. E square limit extending to 0 of e power x minus 1 divided by x, and by that limit formula it becomes 1. E square into 1 is e square. Question 3. Limit extending to 5 e raised to x minus e raised to 5 divided by x minus 5. Let us use substitution. We will take x minus 5 as y. Therefore, x will be y plus 5. And as x tends to 5, substitute x as 5 here. 5 minus 5, y becomes 0. So y tends to 0. Let us change the variable. Limit y tending to 0 of e raised to x is y plus 5 minus e raised to 5 divided by x minus 5 is y. Now it is similar to the previous question. We can separate the powers here. E raised to 5 into e raised to y minus e raised to 5 divided by y. Limit y tending to 0 of e raised to 5 is a constant. It can be taken outside the limit. We have e raised to y minus 1 divided by y. By the formula, this limit is 1. E power 5 into 1, which is e power 5. Question number 4. Limit extending to 0 of e raised to sin x minus 1 divided by x. Let us multiply and divide by sin x. I am rearranging the terms. Let us write e raised to sin x minus 1 divided by sin x times sin x by x. Now let us apply the limits for this term as well as for that term. Limit extending to 0 of e raised to x minus 1 divided by x is 1. And limit extending to 0 of sin x divided by x is also 1. And we know that as x tends to 0, sin x tends to 0. So the formula is applicable. The first term becomes 1. The second term also becomes 1. Therefore, the answer is 1. Question number 5. Limit extending to 3 of e raised to x minus e raised to 3 divided by x minus 3. It is similar to that third question, same type. We will substitute x minus 3 as y. Therefore, x is y plus 3. And as x tends to 3, y tends to 0. Let us change the variable. Limit y tending to 0 of e raised to x is y plus 3 minus e raised to 3 divided by x minus 3 is y. Let us write this as e raised to y times e raised to 3 minus e raised to 3 divided by y. e raised to 3 is common and it is a constant. It can be taken outside the limit y tending to 0 of e raised to y minus 1 divided by y. By the formula it becomes 1. Therefore the answer is e cube. Question 6. Limit x tending to 0 of x times e raised to x minus 1 divided by 1 minus cos x. We have a formula 1 minus cos x divided by x becomes 0. But this formula is not applicable in the denominator. Division by 0 is not defined. Therefore, let us use the identity for 1 minus cos x. One minus cos x is 2 sine square x by 2. This is equal to limit x tending to 0 of x times e power x minus 1 divided by x. I am dividing the numerator by x, so I need to multiply by x, divided by 2 times sine square x by 2. I am dividing the denominator by x by 2 the whole square, so I need to multiply by x square by 4, that is x by 2 the whole square. Now this x square and this x square are getting cancelled. Limit x tending to 0 of e raised to x minus 1 divided by x. Let us simplify this. 2 is getting cancelled, and that 2, write the reciprocal of half, which is 2, divided by, the denominator can be written as sine x by 2 divided by x by 2 the whole square. Let us apply the limit for both numerator and the denominator. For the numerator, we will be using this formula. Limit x tending to 0 of e raised to x minus 1 by x is 1. And for the denominator, we will use limit x tending to 0 of sine x divided by x is equal to 1 formula. And as x tends to 0, x by 2 also tends to 0. So the formula is applicable. 2 is a constant. The numerator becomes 1. The denominator becomes 1 square. Therefore, the answer is 2. Question number 7. Log of 1 plus 2x to the base e divided by x. If the base is not written, it means to the base e in our textbook. Otherwise, in other books, it will be written ln of x. That means to the base e. Let us multiply and divide by 2. And we will use limit x tending to 0 of log of 1 plus x divided by x is equal to 1 formula. As x tends to 0, 2x also tends to 0. Multiply both sides by 2. Therefore, the formula is applicable. 2 is a constant, and by that formula it becomes 1. Therefore, the answer is 2. Question number 8. Limit x tending to 0 of log of 1 plus x cube divided by sine cube x. Let us divide both numerator and denominator by x cube. This is the numerator and the denominator is x cube x divided by x cube. Now we will use the formulae, limit extending to 0 of log of 1 plus x divided by x is 1, and limit extending to 0 of sin x divided by x is also 1, and as x tends to 0, x cube also tends to 0. Let us apply the limit for the numerator. It becomes 1, and denominator it becomes 1 cube. Therefore the answer is 1. Example 6. It is given on the same page. Compute limit extending to 0 of e raised to x minus sin x minus 1 divided by x. Let us rearrange the terms. Limit extending to 0 of e raised to x minus 1 divided by x and minus sin x divided by x. Denominator x is common to all these terms. Now we will apply the limit formulae. Limit extending to 0 of e raised to x minus 1 divided by x is 1, and limit extending to 0 of sin x divided by x is 1. So limit of the first term becomes 1 and limit of the second term is also 1. Therefore the answer is 0. Example 7. Limit extending to 1 of log x to the base e divided by x minus 1. We will use substitution. Let us take x minus 1 as y. Therefore x is 1 plus y. As x tends to 1, y tends to 0. By substituting x as 1 here, we get y as 0. Now let us change in terms of y. Limit y tending to 0 of log of x is 1 plus y to the base e divided by x minus 1 is y. And we have a formula. Therefore this becomes 1. The formula is limit extending to 0 of log of 1 plus x divided by x is 1.